What specific problem does Eso-LMs aim to solve, particularly in relation to the shortcomings of BD3-LMs?
Eso-LMs aim to address two significant shortcomings of BD3-LMs. 1. Mode collapse at low sampling steps, where BD3-LMs exhibit severe degradation in sample quality when the number of denoising steps is reduced, resulting in worse performance compared to both autoregressive AR models and diffusion models, and 2. Incomplete caching, as BD3-LMs only support KV caching across blocks but lack it for intra-block diffusion, limiting overall speed gains. Eso-LMs introduce a hybrid approach that combines autoregressive and masked diffusion paradigms, enabling KV caching during the diffusion phase, which was previously unavailable in masked diffusion models. This innovation allows Eso-LMs to maintain competitive performance in both low and high NFE regimes, effectively mitigating the issues faced by BD3-LMs. Consequently, Eso-LMs achieve faster inference and improved generation quality, setting a new state-of-the-art among diffusion models.
How does the proposed Eso-LM work? Illustrate it step by step, focusing on the hybrid architecture and the training sampling procedures introduced in the paper.
The proposed Eso-LM operates through a hybrid architecture that combines autoregressive AR and masked diffusion model MDM approaches. First, during training, Eso-LM uses a hybrid loss that incorporates both AR and MDM objectives, allowing for smooth interpolation between the two paradigms. The model employs a revised attention mechanism that supports both sequential AR style and parallel MDM style generation, enabling it to generate some tokens in parallel while others are generated sequentially. In the sampling procedure, Eso-LM first generates a partially masked sequence using the MDM, which is then completed by the AR model. This two-stage sampling process allows for efficient KV caching during the diffusion phase, significantly improving inference speed. The model also introduces a custom attention bias matrix that modulates information flow, ensuring that clean tokens can attend to each other while maintaining causal attention for masked tokens, thus optimizing both training and sampling efficiency.
Can you come up with a simple yet illustrative example on how the Eso-LM generates a sequence of text? Walk through the main algorithm steps with your example.
To illustrate how Eso-LM generates a sequence of text, let's consider a simple example where we want to generate the phrase, "The cat sat on the mat." The generation process involves two main phases, diffusion and sequential. 1. Diffusion phase. We start with a fully masked sequence represented as _c_t equals 1 equals mmmmmmmm, where _tem denotes masked tokens. The model first generates a partially masked sequence _c_0 using the masked diffusion model, MDM. For instance, it might produce _c_0 equals the mmmmmm, where they is unmasked. 2. Sequential phase. Next, the autoregressive model, AR, fills in the remaining masked tokens in a left-to-right manner. It uses the clean tokens from _c_0 to condition the generation of the next tokens. For example, it generates cat for the second position, resulting in _c_0 equals the cat mmmmmm. This process continues until all tokens are filled, leading to the final output, the cat sat on the mat. Throughout this process, Eso-LM leverages a custom attention mechanism that allows it to efficiently manage both masked and unmasked tokens, enabling faster inference and high-quality text generation. The model's ability to interpolate between autoregressive and masked diffusion paradigms allows it to adaptively control the generation process, ensuring coherent and contextually relevant outputs.
What are the practical advantages of using Eso-LMs over existing language models, such as autoregressive and masked diffusion models?
Eso-LMs offer several practical advantages over existing language models, particularly autoregressive AR and masked diffusion models, MDMs. Firstly, they achieve significantly faster inference speeds, up to 65 times faster than standard MDMs, and 3 to 4 times faster than KV-cached semi-autoregressive baselines, due to their support for KV caching during both diffusion and sequential phases. Secondly, Eso-LMs maintain competitive generation quality across various sampling steps, avoiding the mode collapse issues seen in BD3LMs at low sampling steps, and they establish a new state-of-the-art perplexity for discrete diffusion models. Additionally, the hybrid architecture allows for fine-grained control over the interpolation between AR and MDM perplexities, enabling users to optimize performance based on specific task requirements. Lastly, Eso-LMs effectively combine the strengths of both paradigms, providing a more versatile and efficient solution for language generation tasks.
How is the effectiveness of Eso-LMs validated in the paper? Discuss the experimental design, datasets, and metrics used to assess performance.
The effectiveness of Eso-LMs is validated through extensive experiments on two standard language modeling benchmarks, the 1 billion words dataset LM1B and Open Web Text OWT. The experimental design involves training Eso-LMs for 1 million steps on LM1B and 250,000 steps on OWT, utilizing a transformer architecture with rotary embeddings. Performance is assessed using perplexity as the primary metric, with results reported on the test split for LM1B and a validation set for OWT, where the last 100K documents are reserved for validation. The paper compares Eso-LMs against leading masked diffusion models, including MDLM, SEDD, D3PM, and BD3LMs, to establish state-of-the-art perplexities among diffusion models. Additionally, the paper evaluates generation speed, showing that Eso-LMs are significantly faster than prior diffusion methods, achieving up to 65 times faster inference than standard MDMs, thus demonstrating both quality and efficiency improvements.
What results did the authors achieve with Eso-LMs, and how do these results compare with previous models, particularly regarding perplexity and inference speed?
The authors achieved state-of-the-art perplexities for Eso-LMs on the 1 billion words dataset LM1B and Open Web Text OWT, demonstrating effective interpolation between masked diffusion models, MDMs, and autoregressive AR models. Specifically, Eso-LM-A outperformed MDLM by approximately 1 perplexity point at alpha_0 equals 1, while Eso-LM-B maintained competitive performance with MDLM at low NFEs and approached AR model quality at high NFEs. In terms of inference speed, Eso-LMs are reported to be 3 to 4 times faster than prior diffusion-based methods that support KV caching and up to 65 times faster than standard MDMs that do not support KV caching. This significant speedup is attributed to the efficient KV caching during both the diffusion and sequential phases, which is a unique feature of Eso-LMs compared to previous models like BD3LMs and MDLM. Overall, Eso-LMs not only improve perplexity, but also enhance generation speed, establishing a new state-of-the-art on the speed-quality Pareto frontier.